You're watching InTechnology, a video cast where you can get smarter about cybersecurity, sustainability, and technology.
Welcome to the InTechnology podcast. I'm your host, Camille Morhart, and I have with me today Chris Kelly. He is Vice President of Client Architecture at Intel and also General Manager of Software Definition and Strategy for Platforms. Welcome to the podcast, Chris.
Hi, Camille. Thanks for having me. Really good to be here.
So we are just going to dive right into a fairly meaty topic. We're going to talk about how endpoints and software are affected by artificial intelligence evolving toward distributed computing. I wonder if you could actually kick us off by providing some context as to this evolution of artificial intelligence into distributed computing models.
It's a really interesting topic. The AI world is undergoing a supernova. It's almost like we're being thrown to the edge of the universe at light speed, trying to keep up with advances in AI. But the AI revolution, which is upon us, is happening on clients now as well. AI models, as they continue to get larger and continue to be refined, we don't believe that those things are going to end up living on the cloud forever. There's a bunch of different reasons for that as they continue to get more sophisticated. They're going to be expensive to be able to transfer that amount of data between the cloud and an edge and an end user and an endpoint. And a lot of end users are going to end up needing very specific, tailored responses or co-pilot trained or inference models that have specific responses or content that they care about, versus you use an AI model or have a chatbot response from the cloud. If you're an enterprise, for example, you want to be able to use an AI model to specifically help engineers design a chip. Or if you're a retailer, you want to be able to have responses as a retail group and that are specific to your own products. You can't really put all that stuff in the cloud and have it be both cheap and private. So privacy and security is an important aspect of AI and clients. So the only way to really make that work is AI models, instead of them only residing in one place in this sort of continuum of cloud edge endpoint, is to be able to have a lot of co-pilots and AI models reside on an endpoint. Typically, I think what will happen is you'll have large models that'll be trained by data center and edge products, and then inferencing will happen on endpoints. We're building capabilities into PCs that will allow that to begin to occur with our next generation product, as work closely with Microsoft to be able to open that up. But the fun part will be a hybrid AI model where you've actually got this one model or a set of submodels that has to spread across the continuum of data center, edge, and endpoint. And ensuring that all that stuff works together is a really interesting sort of hard distributed computing problem.
I assume software is going to solve it. So how is that evolving, or what kind of different models are we starting to see emerge to help orchestrate that sort of hybrid AI as you describe it?
We played around with a couple different techniques. I think there'll be multiple techniques that get used, as typically in tech. We'll experiment a bunch, and then some winners will probably emerge, or some standards will emerge. At Intel, we played around with the notion of extending Kubernetes, which is sort of the existing container technology, open source-ish container technology in data centers. We've done some work to land Kubernetes containers on clients. If you've got a Linux-based client or a device that can talk Linux, like using the WSL2 interface with Windows, it's relatively easy to go do that. And that's one mechanism. If you want to put a model inside a Kubernetes container and you think you can have that reasonably perform, you can extend that then to an endpoint. There's some issues with that. There's some security issues with it on a laptop or a desktop. A Kubernetes container has a tendency to be a pretty large image, and PCs and endpoints generally are concurrent devices. We don't just do one thing, we do lots of different things. So when you layer a Kubernetes container that's like a K3s container on top of a client, other stuff stops working very well. That will be one technique that may be used. The other technique I think that's really interesting, that's emerging in the ecosystem, a lot of startup activity, and will provide potentially some additional ubiquity, is using web workloads and web techniques to be able to then move workload to where user data is. The key thing is not having to move data, right? You don't want to have to move gobs of data. You want to move models and applications, if you will, to where the data exists.
Is that because of latency, or is it because of transmission cost, or is it because of privacy, or all three?
Excellent. All three, right? All three. The data costs, as data explodes, data costs moving data, it ends up being a much larger amount of sort of data bits that you'd have to move if you're moving source data for a model. It just gets prohibitively expensive. And if you're moving data around on a network, the hypothesis is that latency will forever get smaller. But as you approach the speed of light, there's going to be a limit of how fast you can get things from one place to another. Moving the application to the data avoids some of that problem. But I think the most interesting one for us at Intel is the notion of privacy, not just for regulatory reasons, but also the right thing to do reasons. If a particular end user has preferences, or you're inferencing on an individual's end user's preferences to improve the efficacy of an AI chatbot to give you better responses, you don't necessarily want that in the cloud. And if you're an enterprise, you definitely don't want your private, confidential, proprietary information sort of being jumbled into the giant chatbot in the sky kind of thing. Microsoft and OpenAI know this. This is why the creation of specific copilots, for example, for enterprises becomes an important aspect. So all three, Camille, are important to get done. That's right.
What is the status of Moore's Law today?
It's alive, but it's morphed a little bit. The physical aspect of Moore's Law is alive and well and continuing to progress.
What is it? Remind us what Moore's Law is.
Essentially doubling the density of transistors in any given unit area every roughly 2 years. Some years, some generations it's 2, some generations it's a little longer than 2. There have been a couple generations where we've been able to improve even on that. And we can continue to go do that. The advanced EUV techniques that are being used are almost bridging on science fiction stuff to be able to keep the physical aspects of Moore's Law alive. Now, there's a corollary, which we have to acknowledge, which is it is getting more expensive to produce a wafer in order to be able to continue down the path of physical Moore's Law reduction. And there's enough demand and requirements in the industry to continue reducing that cost. But every time you have to jump over a big technology leap, it stands to reason that things will get more expensive, certainly for a time. And for advanced node manufacturing, it's more expensive to make a wafer. How do we compensate for that? So we compensate for that change by using disaggregated technologies, chiplet technologies on package, to be able to then mix and match processes and suit those processes to taste for the products that we need to go make. Think about a microprocessor, an Intel product. It's not just about CPU cores, but we have a bunch of IPs on that particular product, graphics engine, NPUs, a bunch of IO technologies, media accelerators, et cetera. Not each of those IPs needs to have an advanced node on the same pace that, say, a CPU core does, or a GPU may need to. And balance both cost and R&D investment and reuse opportunities. We use a disaggregated architecture to put the right IP on the right transistors. And as costs morph and increase, that way we can also then mitigate having to move everything to an advanced node where you may not necessarily need the advancement of it. So it's funny, we don't often talk about packaging technologies or packaging and test technologies as part of Moore's Law, but in my view, they absolutely are. There's been as many or more advances in advanced packaging through stacked memories, direct attach, die attach technologies, IO that allow for die to sit right next to each other on a single package. There's as much advances in packaging technology to keep the Moore's Law flame alive as there have been just in transistors. And that whole combination, that whole sort of cocktail, makes it such that you can continue to see the advances in Moore's Law generally.
At a high level, what are some of those sci-fi evolutions in actually chip reduction or transistor size reduction?
Everything started out on a single plane. And the high level changes that have happened over the course of the last 10, 15 years have really been twofold. Looking at different, you call them exotic, you could call them just another element of the periodic table, making chemistry changes to base transistors and transistor construction and metal construction. That's sort of number one. The other one is taking that essential planar transistor construction technology and making it 3D. We started using trenches and trench FETs, and now you're starting to see the evolution of transistors where instead of gates and gate technology being only in one plane or in 1.5 planes, you're starting to see a full 3D gate technology where we can get more contact between the gate and the drain and densify transistors, like an all-in thing, Camille. Like, so chemistry, physical construction, metal stack and metallization and deposition of metals. You also have to keep up with that. You have to interconnect all the transistors to be able to get signals in and out of them. Like, I don't work in that part of the company. I work in the design part of the company. I'm always in awe of some of the stuff that our colleagues over in the TMG world come up with and what we're able to do to advance the bow front of fab technology. It's pretty amazing.
That is pretty spectacular. So what other things should people be thinking about or aware of when we think of client computing and moving forward?
I think it's a really exciting time to be working on PCs. If the people have declared the death of the PC many times, and I'm sorry to say they're wrong. The PC's never been a more vital or important device in people's lives, not just through sort of explosion of video conferencing technologies when we all could come into an office, but the PC and the PC platform is where you go to do your most important valued work that you're going to be judged on. The PC is the ultimate Darwinian device. It's a device in the endpoint stack that evolves the fastest, capable of handling and managing through evolutions and changes. And we still believe that to be true. Of course, the number one big change you'll see in PCs over the next 3 or 4 years, we've talked about briefly already, which is the advent of AI capabilities and the AI PC era sort of beginning. If we're honest, you've been able to run AI content, actually AI models on PCs for a while. There's instructions that we built into our CPUs that handle matrix calculation. As the AI supernova continues to pace, we need a lot more capability to be able to run copilot models and helper models, transformers. I don't think we're not even in the middle innings of AI evolution on PCs. We're just beginning the game, if you will. And so that'll be the big change that happens over the next 2 or 3 years, Camille, is adding AI capability, adding end user and developer capabilities to develop on them. AI is an enhancement or a horizontal augmentation to all the things that you do with your PC today anyway. You'll have AI enhanced video effects to be able to make people like me look way better than we do when we talk about stuff like this, to allow you to make, whether it's presentations or Word documents or code, the work that you do and the workflow that you do will end up being enhanced by AI enhanced functions. So AI is not like a new application class on a PC so much as it is a augmentation to workflow, where then that will be able to spawn either new end user applications, it'll be able to spawn new ISV value as they add AI to their existing workflows. The thing that gets me the most excited about AI and PCs is to see what our ISVs are going to do with it. Once the capability exists and you can count on having an NN or the ability to run a model on a PC pretty regularly, what are our ISVs going to do with the capability that we provide? I think that's the most exciting thing.
Being independent software companies. Yeah.
Yeah, ISV means independent software vendor. Yeah, sorry for using the jargon, but yeah, that's right. Adobe, Autodesk, the web and web workload folks that are making apps on the web using web APIs, all of those applications will be enhanced by AI capabilities locally on a client. And that's the exciting thing.
Chris Kelly, VP of Client Architecture and also GM of Platform Software Strategy and Development. Great to have you on the show. Thanks for joining us.
Thanks for having me, Camille. Good to see you, and be well. Take care.
Never miss an episode of InTechnology by following us here on YouTube or wherever you get your audio podcasts.
The views and opinions expressed are those of the guests and author and do not necessarily reflect the official policy or position of Intel Corporation.